Hi everybody, this is Mrs. Buchanan and this is my first blank wall and I am blank walling over chapter 15, 15.1 and 15.2. So let's talk about acids and how we name acids. This should be review. If you do not remember anything, please go back and check out chapter 3 about naming. So I already wrote some stuff on the notes. So how do you name acids? First, there are two types of acids, one being binary and the other being oxy. So let's talk binary first. So how do you tell if it's a binary acid? Binary acids are a hydrogen plus one other element. The anion ending, sorry about that. The anion ending for a binary acid is IDE. We use the prefix hydro, and then the suffix will be IC. So, for example, a binary acid would be hydrochloric acid, HCl. Another example one would be HBr, hydrobromic acid. Okay, the next type of acid is an oxyacid. So what are you looking for? You're looking for an oxygen in the formula. Oxyacids always begin with hydrogen, but they're usually paired with a polyatomic ion. They're usually paired with a polyatomic ion that ends in ATE or ITE. So the first one we're going to talk about is ATE. So the anion ending is ATE. The root of the name and the prefix would be, and then the suffix would be IC. 8 goes to ic. So sulfuric acid, phosphoric acid. Those endings were phosphate for phosphoric acid. Sulfate goes to ic. That's sulfuric acid. Nitrate, that would be nitric acid. So just remember the ending 8 goes to ic. That's an oxyacid. The next type of oxyacid is the polyatomic ion that ends in ITE. So you again use the root of the name. In an oxyacid, you do not name the hydrogen, even though it's in there. So you use the root of the name, and you change the ITE to OUS. So nitrite would go to nitrous. Sulfite would go to sulfurous. So there's a couple examples. Below, let me move this, but below you can take a few minutes and see if you can figure out what the formulas and the names are, and then pause the video and come back and check your answers. So check your answers. Here we go. Sulfurous acid is H2SO3. That's an oxyacid. Hydroiodic acid. Notice that we have the hydro in there. The hydro, we're naming it, so that's a sign that it is a binary acid. Then we have perchloric acid, the third one, that is an oxyacid because there is no hydro in there. Also, now we're looking at the formulas and we're writing the name to them. So HNO2, notice the oxygen in there, that will be an oxyacid. So NO2 is nitrite, so it will go to nitrous acid. PO4, phosphate, 8 goes to ic, so it would be phosphoric acid, and C2H3O2 is acetate. Acetate goes to acetic acid. Now, what do the formulas for acids have in common? Hopefully you figured this out. They all have hydrogens. Generic formula for an H and then an X. The X can either be a monoatomic ion or a polyatomic ion. So let's talk about the nature of acids and bases. Acids, the properties. You should be pretty familiar with this. You've had this in honors chem, you've had this in biology, but acids, they have a sour taste. Citric foods, that's an example of a sour taste. Candy has a sour taste because there's lots of citric acid in it. They also have the ability to dissolve metals. That's why your chemistry teacher tells you not to throw acid down the sink. It will dissolve the copper pipes. It will also turn blue litmus paper red, and it has the ability to neutralize a base. Some examples of an acid are HCl, hydrochloric. You'll find hydrochloric acid in cleaning products. You'll find them in uh, several things. H2SO4 you can find in batteries. Nitric acid you'll find in fertilizers. Citric acids, like I said, fruit juices. And acetic acid you can find in cleaning products. That's vinegar. So acids are all around us. I believe I spelled neutralize wrong, so I apologize for that. I just noticed that. So let's talk about bases. Bases are pretty much the opposite of acids in terms of their properties. They have a bitter taste. If any of you had your mouth ever washed out with soap, you know that it was bitter when you were younger, or tasted soap. It has a very bitter taste. Also, it has a slippery, bases have a slippery feel. Soap is made of a base. So that's why when soap gets wet, it gets really slippery. It's because it has some base properties in it. It will turn red litmus paper blue, and it will also has the ability to neutralize an acid. Bases are used to neutralize your stomach acid. If you have an upset stomach, we use bases to neutralize that. Um, so let's talk about some of the things. Sodium hydroxide is a example of a base. It's used in soap and plastic making. Potassium hydroxide, it's used in electroplating and again, soap production or batteries. Sodium bicarbonate, we use it in food, baking soda. We use it in acids. Some people used to use baking soda to brush their teeth. Ammonia is used in fertilizer, cleaning products. So bases and acids and bases we use all the time. They're in our everyday life. So let's talk about the definitions of acids and bases. We're going to focus on two of them. There's actually a third, but we're not going to focus on that one. Arrhenius model, which was developed by a Swedish chemist in the 1800s. He actually was working on conductivity experiments, and this is how he came across this definition for acids and bases. It's a very constrictive definition. It only fits certain compounds, so that's why we have more than one definition. So let's talk about the definition for an acid. Acids produce hydrogen ions in aqueous solution. So what you're looking at here is hydrochloric acid, and it's dissociating into water. And when it dissociates, it breaks down into hydrogen ions and chloride ions. What happens is that hydrogen ion bonds to form to the water and forms an H3O plus ion, which is a hydronium ion. You see that in some books. They really focus, we'll talk more of that in the Bronsted-Lowry, but we're looking at how that hydrogen just dissociates off of the hydrochloric acid. So pretty simple definition. So let's talk about B. Bases, the definition for a base is they produce hydroxide ions in aqueous solution. So you notice here you have sodium hydroxide, and sodium hydroxide dissociates into sodium ions and hydroxide ions, which what this definition is saying is that the only thing that can be a Arrhenius base is something that produces hydroxide ions or has hydroxide ions. So this is a very narrow definition. So we're going to go on and we're going to move on to the Bronsted-Lowry model. So the Bronsted-Lowry model is a much broader definition, especially for bases. And the definition of an acid is the acids are proton donors. So what's a proton? A proton is an H plus ion. So what happens is when the acid is in water, it donates its hydrogen ion to the water, forming a hydronium ion. So that's the definition. It's a donor. It donates that hydrogen ion, and then that chloride ion goes off by itself. I would say by itself, but it's in solution. So that is an example of an acid as a proton donor. Bases, which this is why most people like this definition because there's a lot of other bases. There are a lot of other compounds that are considered to be bases, but they don't have OHs in them. So this is why this definition is widely accepted. Bases are proton acceptors, which means they have the ability to accept a proton. So the H, the NH3 over here is going to accept that proton from the HCl, and then that's how we get the NH4 plus, the ammonium ion. You recall me earlier talking about the hydronium ion that is formed from water in solution with the hydrogen ion, and it forms the hydronium ion. So I apologize if I fade in and out. My microphone is not the best here. So let's talk about conjugate acid-base pairs. This belongs with the Bronsted-Lowry definition. So a base, remember, is a proton acceptor, and an acid is a proton donor. So if you notice, the definition of a conjugate base is what remains after an acid has donated a proton. So the acid in this example up here is HCl. So HCl, the H and the H is going to donate its proton to the water, and the Cl is going to be your conjugate base. It's losing that proton. So it's the conjugate base is the one with the one less proton. A conjugate acid is what is formed when a base accepts a proton. So the conjugate acid is going to be the compound with one more proton on it. So you notice that the water accepted the hydrogen from the hydrochloric acid, and the conjugate acid would be the hydronium ion. I want to bring something up here. Water can behave as both an acid or a base. It can either accept a proton or it can donate it, depending on what water is paired with. So when water can behave as an acid or a base, we call that amiphoteric, and that's just something you should know. I believe most teachers talked about it in honors chem. So let's look at your example. It says find the conjugate acid, the conjugate base in each equation. So first go through and mark what's your acid and what's your base. So HCl is your acid because it is a proton donor, and your water in this case is behaving as base because it is a proton acceptor. So now go back and look at your definitions and try to figure out which one is the conjugate acid and the conjugate base. It doesn't matter which one you do first. So remember, the definition of a conjugate base is what remains after an acid donated a proton. So that should lead you to Cl negative is your conjugate base. So then H3O plus will be your conjugate acid. So take a moment and try the next example on your own. Pause the video. So here in problem number two, the acid is HCl, the base is NH3, the conjugate acid is NH4 plus in this case because it is what's formed when a base accepts the proton that has the one more proton, and the conjugate base here is the chloride ion. So in number three, it says, what are the conjugate acid-base pairs? So if you have an acid, which the acid on number one is HCl, what would be its pair? Who would it pair up with? So the HCl, which is the acid, the HCl, which is the acid, would mean that the Cl negative would be the conjugate base, and the water here would be the base. So its conjugate acid pair would be H3O plus. And then what are the conjugate acid base pairs in number two? Again, the acid is the HCl, the chloride ion is the conjugate base, and the NH3 is the base, and the NH4, and that is a mistake, should say conjugate So problem number 3 says, in each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. So take a couple minutes, try to figure these out, and then so while you're doing that, pause the video and then come back and check your answer. So in number 1, H2SO4 is the acid, then water is the base. So the conjugate base here would be HSO4. And the conjugate acid would be H3O plus. And then number 2, the HCO3 negative is the base. And then here the water is the acid. So like I said before, water can behave as an acid or base. So it can be what we call amiphoteric. H2CO3 is the conjugate acid because it gained that proton, and the conjugate base would be OH negative because it has one less proton. You'll notice I have lines going across connecting the acid to the conjugate base. This is your acid conjugate base pairing. This is how they're paired up. That's why I wrote the lines like I did. It's done the same way in your textbook. So let's look at problem number 4. It says write the formula for the conjugate acid. Remember, in order to be a conjugate acid, you have to have one more proton. So you have Br negative. So I'm going to add a proton onto that, and that makes it become HBr. So SO4 2 negative, sulfate. When I add another hydrogen ion on there, it will become HSO4. And the charge becomes a -1. Why is that? Because I added that one extra proton on there. So that +1 takes away, adds to that -2, and that's how we have that -1 charge. So NH3 is neutral, so when I add another proton onto there, that means I'm going to have an extra +1 charge. So therefore, it's going to be NH4 plus. So look at number 2. It says write the formula for the conjugate base. So that means we need to take a proton away. So HNO2, taking that proton away, now becomes NO2 negative. B, HSO3, again, taking the proton away, the hydrogen ion away, that SO3, then taking that away, the answer would be SO3 -2. And then letter C, take a minute, see if you can figure that out on your own. The answer would be NH2 negative. So problem 5, it says which pair is not a conjugate acid-base pair? Pause the video, see if you can figure out which is the correct answer. The correct answer is B. In order to be a conjugate acid-base pair, the two substances have to be related to each other by a transfer of a proton. A and C, they're transferring the proton. And B, there's no transfer of the proton. They just change the polyatomic ion. So I hope you learned a lot, or I hope I didn't put you to sleep anyway. So thanks for listening to my first Blankwalle. I'm sure you'll hear me again soon. Have a great evening.